Yeah, good afternoon, girls.
Good
Shall we
afternoon,
start?
ma'am.
Good afternoon, beta. Yeah.
Yes,
Last lecture, we have seen the pin diagram of 8085, right? So today we'll see the description of the pin diagram, right? There is a 40 pins I see, as we have explained in yesterday's lecture. That all the pins are divided into the different functionality, like SID and SOD. These are the serial input output ports. These are the trap ports, external initial signals, that is trap RST 7.5, RST 6.5, RST 5.5, and INTR. This is a acknowledgement. And these are the ready signals, ready, hold, and reset in. These are the acknowledgement signals from microprocessor to the other peripheral devices. Plus 5 volt ground, and then the clock is generated. Here we will see the functionality of each and every pin. This is reset out and clock out. This is for the other peripheral devices. These are the control and status signals: write, read, IOM, S1, S2, ALE, address, latch, element. These lines are demultiplexed AD0 to AD7, right? These are differentiated with the help of ALE signals, right? And these are the higher order address line, that is A8 to A15, right? This is the functionality of your microprocessor now. Next, as we have seen, whole pin diagram is divided into the six group: address bus and data bus, status signals, control signals, interrupt signals, power supply and clock, reset signals, DMA request signals, and serial IO signals, right? Whole your chip is divided into the six groups, that is address, data buses, status signals, control signals, interrupt signals, power supply signal and clock signals, reset signals, DMA signals, and serial input output signals, right? These are the address pins. Total address pins are the 16 address pin, that is A0 to A15, but that is divided into two parts: A8 to A15. This is MSB, higher order address, A8 to A15, right? This is unidirectional, no multiple functionality on this pin. But in A0 to A7 is multiplex pin. It is used AD0 to AD7, when it will be used A0 to A7, when it will be used D0 to D7. So lower address pin is multiplex with the data lines, that is D0 to D7, right? These are the bidirectional because data is coming and going out. Address is only going out, it is pointing to the address, right? So this is the lower address pin and the data pin, right? The data buses, to save the number of pins of lower address. Why this is multiplex? Because first we send the data address, and then second stage we send the data. So unnecessarily again 8 pins are increasing into your architecture of microprocessor. So that pin has demultiplex with A0 to A7 pins. So it is just miniaturization of your IC. To save the number of pins, lower address pin are multiplexed with the 8-bit data buses, that is a bidirectional. So the bits AD0 to AD7 are bidirectional and serve as the A0 to A7 and D0 to D7 at the same time, right? So during the execution of instruction, these lines carry the bit address bit during the earlier part of first T state, and then the second T state it will carry the data, that is the identification. First T state it will carry the address, second T state it will carry the data, that we will see in next lecture also, right? The status pin, there are three status pin: ALE, address latch enable, S1 and S0. Now address latch enable used to demultiplex the address and data buses. Which address and data buses? AD0 to AD7, right? If ALE is 1, when AD0 to AD7 lines have an address, right? If ALE is 1, 1 means what? It is an active high. So that time your signals is carry only address which A0 to A7. If ALE is 0, that time your signals will carry the data. When it is a low, it indicates the contents are data, that signals is carrying a data. So ALE is demultiplexing between, or it gives the identification between AD0 to AD7, right? So when ALE is 1, that means that line is act as a A0 to A7. When ALE is 0, that line is act as a D0 to D7. These signals can be used to enable the latch to save the address bit from the AD lines, right? Now the second is the status signal, that is S1 and S0. These are the status signals. So it gives the status what microprocessor is performing now, right? If status signals both are 0, 0, your processor is in a halt mode, right? If it is a 0, 1, your processor is in a writing mode, right? if it is a if it is a 1, 0, your processor is in a reading mode, data reading mode. And if it is a 1, 1, your processor is in a fetch mode. It is a fetching a instruction and it is giving to the instruction decoder, as yes we have seen the yesterday's and day before yesterday's lectures, right? So these are the status signals. Now these are the status pin. ALE, S1 and S0 are the status pin. Now it is a control pin. Which are the control pin? Write, RD, WR, IO, M bar. Now write means what? Your microprocessor is read means what? Your microprocessor read memory or input output devices. This processor is reading a data from your input output devices or the memory, right? Input output devices means what? It is a keyboard, means processor is reading a data from the keyboard, right? If it is a mouse or any other devices, temperature sensor and all, the processor is reading a data, so it is a read mode, right? Write mode means it is processor is writing with the memory into the memory or output devices. So memory can read, the microprocessor can read the data from the memory, microprocessor can write the data from the memory, as well as input output device. From input microprocessor will read and output microprocessor will write, right? Now the second control signals, IO M bar. Suppose these IO M bar signals are active low, that means your operation is in with the input output devices, right? This is the active low signals. IO M bar is equals to 1, means your operation is only with, means processor is reading from the input devices and processor is writing to the output devices, right? So this IO M bar is differentiated whether your microprocessor is performing operations with input output devices or the memory, right? So IO M bar is equals to 0, means the address on the data bus is for the memory. It will use for the memory. So this signals is giving the control signals. Now these are the statistic what it is given over there. Suppose IO M bar is 0. If it is a 0 means memory operation, means processor is doing a operation with memory. Our read bar is also 0, write is 1. So what it is? It is reading a data from the memory, right? So IO M bar is 0, read is 1 and write is 0. Write is 0 means what? It is a writing a data into the memory, right? So IOM bar is 1, means no operation with memory, it is only with input output. Read is 0, means it is reading a data from input devices. And the last is that if IOM bar is 1, 1, that means if it is a 1, 1 means It is a writing into the output devices, right? So these are the differentiation, and these are, you need to know that MEM RD bar, MEM WR bar, IO RD bar, it is D is put it here, IO WR bar. So what is this performance is that you should know that. Now this is the control and status signals combined. When S0 S1 is combined with IOM active, we get the status machine cycle, right? This is very important for the machine cycle. If IOM bar is 0 means operation with memory, means your program is in a memory, and both 1 S0 S1 means it is fetching a opcode, right? But RD is equals to, fetching means you are reading from the memory, but S0 S1 is 1 means it is fetching a opcode and it is giving to the instruction decoder, right? So suppose IOM bar is 0 1 at, it is means it is reading from the memory, your data is reading from the memory, and 001 means you are writing into the memory. So this is very very important, you should differentiate it. Suppose IOM bar is 1 means all this operation is with input output devices, right? So now S0 is 0 means what? It is writing, reading from the input devices. S1 is 0 means what? It is writing into the output devices. And if 1 and 1 0 is there, that means what? This condition is interrupt acknowledgement. If this is 1, right? This is interrupt. And then these are the unidentified halt, hold, reset and everything. But this is very important. This is 1 actually. This is very important. It gives the status, what is the operation is going on into your microprocessor, right? Now these are the interrupt signals. Next these things is, they are signals initiated by the external devices to request the microprocessor to do the particular task or work. These are the 5 hardware interrupts, that is all are input signal. It has the highest priority. Trap has the highest priority. Second highest is 7.5, RST 6.5, RST 5.5, INTR. And these are the acknowledgement key that we have accept the trap interrupt signal, and now it is acknowledging to the others ki, yes, I have accepted. So this is the acknowledgement signals. One receipt of the interrupt, microprocessor acknowledge the interrupt by the active low signals, that is INTR, interrupt acknowledgement signals. Anything is, suppose if you get the register tuple, so what you will, one acknowledgement is there, so that postman will take it back and then the send it to the who has sent the send the letters. So that sender will come to know, yes, my letter is received to the particular person and I got the acknowledgement. So this acknowledgement is signals is also the same, that my interrupt has accepted microprocessor and microprocessor has sent me the acknowledgement. So this is the acknowledgement signals, right? Power supply signals, VCC and VS. This is pin number 14 is a plus 5 volt DC supply. It requires the DC supply signals, right? And pin 20 is a ground signals, right? And there are 3 important pins in this group, that is X1, X0, right? These are the crystal pin. This is X1 and X0. Your microprocessor has the X1. It generates the frequency when you, what kind of crystal? This is the crystal oscillator is used here. The crystal frequency is, it is used 6.14 megahertz. So it generates the frequency is 6.14 megahertz divided by 2 means your microprocessor will work as 3.07 megahertz operating frequency, right? So these are the very steady frequency. So crystal RC network, LC network connected to the frequency to the internal. The frequency is initially divided by 2, and since the basic on the timing frequency, so 3 megahertz or a 6 megahertz crystal is connected x1 and x2. It is depend upon that, right? So these are the crystal. It is generated the frequency at what clock pulse your processor should be work. So clock out signal is also same, because in your processor other peripheral also interface. That peripheral also has to work with the same clock frequency. So the crystal is generating a frequency for microprocessor, and the same clock frequency clock out signal is giving to the other peripheral devices which are connected to the your microprocessor. So the clock out is used as a system clock for the peripheral devices, and then it is used for the other peripheral devices, right? So reset in, this is the reset signal. So reset in means input active low. This signal is used to reset the microprocessor. The program counter inside the microprocessor is set to 000, and buses are tri-state, means everything, all the data will reset, and then it is tri-state, but your buses will be a tri-state. But when it is a reset in, is your microprocessor is reset, the same as microprocessor will generate the reset out signal to your peripheral. That peripheral system also the reset, right? So that is the input signals to the your peripheral. So the reset out signal, it indicates that microprocessor is began reset, used to reset all connected devices when the microprocessor is reset. Suppose if you reset your computer, so automatically your keyboard also reset, your monitor is also reset. So what it does, your microprocessor will generate the reset out signal to the keyboard, to the monitor. So the simultaneously your monitor is also reset, your keyboard also reset, right? So that signal, reset out signal, is used. Now the DMA request signals. DMA means what? It is a direct memory access. When two or more devices are connected to the common bus to prevent the devices from interfacing with each other, tri-state gates are used to disconnect all the devices except the one that is communicated at that given instant, right? CPU controls the data bus operated between the memory and IO map. DMA operation is used for large volume of data transfer from memory to input output devices directly without involving the CPU, right? Otherwise is always input keyboard data, it goes to the this processor, and then the processor will store the data into the memory. So unnecessarily it is an indirect route. If I am storing a data from keyboard to the memory without involving the CPU, so the whatever the controls of bus, the data bus and address bus, it will hand over to the DMA, and DMA will manage to transfer the data from the keyboard to the memory without involving the CPU. So what simultaneously two work can be done it, one is transferring the data, other is CPU can performing their own task without using a address and data line. So that for that purpose it is used the DMA signal. So it is used hold. These signals indicate the other devices request the use of address and data buses. So it use the buses as soon as the current machine cycle is completed. So microprocessor will, when the DMA will send the signal hold to the microprocessor will complete the current cycle, and then it will send the acknowledgement signal to the DMA. Now I have released my data bus and the address bus to you. Now you can utilize the data bus and address bus to transfer the data from memory to input output devices. So hold acknowledgement is also used for that. So microprocessor resign the bus after removing the hold signals. On the receipt of the hold signal, microprocessor acknowledge the request of by sending the hold acknowledgement signals and level out the control buses, right? So there are two signals into the DMA. DMA means direct memory access, the hold and hold acknowledgement. Hold means what? Now I am using your address and data line to transfer the data from memory to input output devices. So the microprocessor will accept the hold signal from the DMA, and now microprocessor will release the signal hold acknowledgement to the DMA. When the DMA will get the hold acknowledgement, the DMA will start working directly, transferring the data from memory to input output devices without involving the processor. Now the serial input signals. These pins are used for the serial data communication, that is SID, serial input data. It is the data line for the serial input. Up to now, this is data line and the address line, and transferring the data from memory to the input output device, from memory to microprocessor. It is into the parallel mode. Simultaneously 8-bit data you can transfer, but in serial mode it will transfer the data one bit at a one time clock pulse, right? So used to accept the serial data bit by bit from the external devices. The data on this line is loaded into the accumulator bit 7 whenever or RIM. There are the two instructions set, RIM and SIM. So RIM instruction is executed, right? So SOD pin means what? Serial output data. Microprocessor is outing a data in other devices in the form of serial mode. It is a data line for the serial output used to transmit the serial data bit by bit to the external devices. The seventh bit of the accumulator is obtained SOD line when the SIM instruction is executed, right? For SID, it is used RIM instruction. For SOD, it is used SIM instruction. We'll see in the later on when it is comes to the instruction mode, right? So external initiated signals, ready. Ready signals are there. This is the input signals to the microprocessor. Memory and input output devices will have slower response compared to the microprocessor, right? Even though we send the clock out signals, right? Still, before completing the present job, such a slower peripheral may not be able to handle the further data and control signals from the CPU. The processor set the ready signal after completing the present job to access the data. It is synchronized the slower peripheral to the processor. Means it is synchronizing both the signals. Yes, Baba, I have done it, my work. Now you can give me the other task. So both the devices is working with their own these things. So it is ready signals will synchronize the devices, interfacing devices to perform their own task. The microprocessor enters into the wait state. Wait state means what? S0 and S1 is 1 while ready pin is disabled. Suppose S0 S1 pin is 1 means it is into the wait state. So that time ready pin is in a disable, right? So waiting stage ready pin is disabled. That's the important of the ready pin. 8085 programming register and programming model. These registers are programmable and able to use all 6 general purpose register: A, F, PC and SP. A means it is the accumulator. This is the 6 general purpose register. A means accumulator, F means flag register, PC means program counter, SP means stack pointer, right? So the accumulator, it is a 8-bit, it is combined with the flag register 8-bit. As yesterday we have seen the flag register format. So carry, auxiliary, parity, sign and zero flag, right? So this is the 8-bit, this is also 8-bit. This gives the status of operation after the ALU, right? B and C register both are the 8-bit. 8-bit, if you use in a pair, it will be used as a 16-bit. D and E register individually, it is a 8-bit. 8-bit, if you are using a pair, it is a 16-bit. DE pair. HL. HL is also the individual register. If you are using a pair, it is used 16-bit. Stack pointer, program counter. So data bus 8 line and 16 bus is going out, right? So this is the programming register. When we perform a program, that time we will see how we will use this programming registers, right? Now fetching and execution cycle. So we will understand first, because there has a mnemonics, there has a data. So how it is identified which is the data, which is the mnemonics, it is fetching the cycle. So now there is a machine cycle. It perform one instruction, that the completion of one instruction, it is called the machine cycle, right? That machine cycle has a two type. It is a fetching cycle and execute cycle. Fetching cycle means it's fetching a data from the memory to the microprocessor, and microprocessor has to understand whether it is a upcode, whether it is a data, whether it is a performance, or what to do with this data, right? The fetch cycle takes the instruction required from the memory stored, and it is an instruction register. It is giving into the instruction register, as we have seen into the architecture, right? Move the program counter on one, so that it points to the next instruction. Program counter automatically, first instruction is fetch, the program counter is automatically incremented by one, and it is pointing to the next instruction to ready to fetch, right? So that is a fetch cycle, right? Execution cycle, actually action which occur during the execution cycle of an instruction, depends on both the instruction itself, the addressing mode specific to use to access the data that may required, right? It has a addressing mode, 1 byte addressing, 2 byte addressing, 3 byte addressing, as we are seeing. So on that byte of addressing mode, how much machine cycle t state is required in that machine cycle. So you are going to clear in this lecture, right? Now fetching an instruction, steps 1. Instruction pointer. This is the instruction pointer, right? Program counter, that is called as a program counter. This is a PC register, right? Hold the address of the next instruction to fetch, right? It is a memory location, contents of that memory location. So it is a, in your program counter it is 001. So it is, this is into your program counter, what it is fetching, 0f, and then automatically you are, after fetching this, your program counter is automatically incremented by 1, and it will pointing to the 0002, right? Now this memory location and content, the content of the program counter are passed across the address line. It is passing a address line, program counter, and it comes to here, right? And then this is memory access register, and after memory access register it goes to the here, up to this, it is this is 0ff, this content will come to the data, this is data, and this is a address, right? And then F00 into the instruction register, it is a instruction, right? This is a memory address, this is the instruction. So instruction register will decode what to do with that. The steps of data flow when the instruction code is 0100111 This is the instruction that move C comma A, means the content of accumulator is transferring into the C, stored into the location 2005H. Now this is a memory, right? This memory, this is your data lines, right? This is a bidirectional. This is a address line, right? This program counter has a address bus, that is a 2005. Each and every memory cell has its a unique address. In memory cell there is a data, right? In if you are sending any letter, so in the envelope there is a address, and inside that there is a letter. So letter is your data, right? That is the information. The same as covering is your address, the same as covering here your address, and inside that address there is a data. So what we want that data, right? So this is a upcode. means what? 4F. It is stored into this. So program counter will send 20005 and it will search in 2005. There is a 4F. This 4F will come to here into the instruction decoder. Instruction decoder will decode, right? The what to do. This 4F means transfer the accumulator data into the C register. Now see, the fetch the cycle to fetch the byte. The microprocessor need to identify the memory location 2005 and enable the data flow from the memory. Now it is enabling the data flow. Microprocessor place 16-bit memory address from program counter to the address line. पहिली steps. Second steps is control unit sends the RD signals to enable the memory chip. RD is also because you have to read. IO M bar is also 0, that is you are performing the operation with the memory. The byte of memory locations is placed on the data byte. यहाँ पे 4F आ गया, ऐसे ऐसे move हो रहा, इधर आया 4F. The byte placed into the instruction decoder of the microprocessor. Task is carried out according to the instruction. यहाँ पे डिकोड करेगा वो समझेगा कि what has to do with 4F. 4F means for his understanding to transfer whatever the data into the accumulator into the C register. So the data will copied from accumulator to the C register. That is our outcome, right? Now the timing and transfer the byte from memory to microprocessor. These are the T state, right? Upcode fetch. How it is fetching a upcode. 4F is a upcode. We are just fetching a upcode, right? This is T1, T2, T3, T4, right? These are the clock signals, complete clock signals, right? Now, how a data byte is transferred from memory to microprocessor. It shows the 5 different group signals clock. The first step. At the T1 is higher order memory. The address is 20 is placed A8 to A15, right? What address was here? What address was here? 2005. So 20 is A15 to A7, A8, and A7 to A5, A0 is 05. This is 16-bit address. So it is divided into 2. So the 20 is in a higher address line. This is a higher address line. And 05 is in a lower address line. When ALE signal is high, so AD7 to AD0 will act as a A7 to A0, right? So this is when ALE signals goes low, this AD7 to AD0 will act as a D0 to D7, and the data from the memory it will fetch into this. So that time your read signals will go active low, right? So whatever the operation, your status signals IO M bar is equals to 0, S0 is equals to 1, S0 is S1 is equals to 1. Means it is a fetching a upcode, not the data. If it is understood microprocessor, S0 and S1 is 1, so it is fetching a upcode. So whatever the upcode it has, it goes to the instruction decoder and it decodes and it analyzes, and according to that task should be performed. So this is called the machine cycle, right? Now we'll read it this. The step 1, T1 higher order memory address 20 is placed on the A15 to A18. This is A15 to A18 higher order lines, right? The lower order memory address is 05 is placed by the bus AD7 to AD0, and ALE signal is high. As we have seen that ALE means address latch enable. It is identifying that whether it is an address or data on AD0 to AD7. So now if ALE signal is high, that means it is a address A0 to A7, right? So the 05 is there. Then next clock cycle it goes lows. Now this AD0 to AD7 will act as now onward it is D0 to D7, right? During the T state 2, RD signals is sent out and the RD signal is active low during the 2 clock period. It is an active low signal. That means it will start reading the data from the memory, right? During the clock cycle T3, this is T3. The memory is enable the instruction byte 4F is placed into the data and transfer the microprocessor. When the read goes high, it causes the data bus to go to high impedance state, right? During the T4, machine code or the byte is decode the instruction decoder and contain the copy A into the register C, right? This T state, this cycle, it will perform the operation. So this is called the machine cycle. For the upcode fetch, those are having only one byte of instruction, right? Now buses structure, right? The various input output devices and memory are connected to the CPU by the group of buses. So this is 8085 microprocessor. 802A15 are connected to the memory. It is 8-bit pins are connected to the input devices and it is output devices. D0 to D7 data buses are also connected to the input memory. Also it is comes from the input, also it is going to the output. And the control signals are connected to all the devices, right? So this is the bus structure of 8085. Nothing, there are the three kind of buses: address bus, data bus and the control bus, right? So this control bus means your IOM bar, S0, S1 read write, right? S0, S1 generally it gives the status to the microprocessor, whether the data is fetching, whether the code is fetching, whether the reading, whether the writing mode, right? As we have seen that. Demultiplexing AD0 to AD7. So now as we have seen that AD0 to AD7 को कौन demultiplex करता है? Address latch enable, right? So AD0 to AD7 lines are served dual purpose. It is a dual purpose obviously. कभी वो एक बार A0 to A7 address line use होता है, कभी एक बार AD0 to D7. So these lines are the dual purpose line, right? So that they can need to be a demultiplex to get all the information. The higher order bit 20 of the address is remain on the bus for the 3 clock cycle, because that is not dual purpose. A15 to A18 lines are only for the address, so it is not the dual purpose. It will be the remain same data 20 on 3 clock pulse. However, the lower address bits 05 remain only 1 clock pulse period and they would be the lost if they are not saved extremely, right? The lower address bit of the address disappear when they needed most, right? To make sure we have to enter address for the full 3 clock pulse, we will use external latch to save the value of AD0 to AD7, right? When it is carry the address bit, right? We have used the ALE signals to enable this latch, and ALE signals is connected to the enabling ground pin to latch the signal. So there is a tri-state buffer. Buffer means what? It will store the 1 bit of memory. So this A0 to A7 will store into that latch and it will be remain for 3 clock pulse. So you are not going to lose your address pin, address data, right? Now see this. Give that ALE operation as a plus during the T1. ALE is high, latch is transfer, out changes according to the input. So during the T1, output of latches is 05. Now see, it is AD0 to AD7 it comes. So each and every has a D clock pulse. It is a enable. This is a latch. So what it is in when ALE is high, it will latch and it will store the data into this pin, right? And next clock pulse, this is latch, your data, whatever the data will come, that is D7 to D0, it will by forget on these lines. So it is a D0 to D7. When ALE goes low, the data byte 05 is latch. When it is a latch, it goes low, right? Only one clock pulse has high and then it goes low. When it is goes low, this data will latch here, it will store. So what, 2005 will be remain as 3 clock pulse, and for next operation this D0 to D7 will perform the operation in this way, right? So the next ALE output of the latch, it represent the lower address line buses A0 to A7 after the latches, right? Generating the control signal. This is also the external control signals is there. The signals are used for the both memory and input output devices related operation. So the four different control signals are generated by combine the signal write, read and IOM bar, right? So MEM bar, RD bar means reading from the memory, it is writing into the memory, it is reading from the input devices, it is writing into the input devices. So with these three help the signals, we generate the four signals as we have seen that. So this is what the specific address latch enable. So it is A0 to A7 and it is comes to the D0 to D7. Same as IOM bar, RD bar, WR bar generating the four control signals, what kind of operations is performing, right? Now instruction decoding and executions. Assuming that A has 87H, the instruction move C comma A means 4F is upcode is fetches. The least steps of decoding the instruction, how it will perform the instruction, right? Place the content of data bus 4F into the instruction register. यहाँ पे डाल दिया 4F, अभी अपना it decodes the instruction. Transfer the content of accumulator A2 into the C, right? दूसरा काम क्या होगा, ये जो A2 है वो हमारे accumulator में है, वो हमारा ये इंस्ट्रक्शन दे रहा है 4F का मीनिंग ये होता है कि जो भी अक्यूमुलेटर में डेटा है वो कॉपीड होना चाहिए सी में. सो इट इज कॉपीड 82 into C and transfer the content into the temporary register to the C, right? So it is accumulator data is transferred into the temporary register and temporary register will transfer into the C. By indirectly our accumulator data is transferred into the C, right? This is it. Now in next